Okay, so I guess I can just say, let's talk about derivatives. Let's do this. Oh yeah, well, I'm not in Python. Three, here we go. We have a. Alright, so so the definition of a derivative is roughly df, or the rise over the run where the limit goes to 0. Okay, but the point here is that we can do what's called finite differencing. So we can we could compute, let's say, then, and then we'll just say, so we're computing it not symbolically but numerically. So let's just say keep them floats. Okay, so now we have x plus h minus y plus f of x, y. We can numerically compute a derivative. Okay, that's a huge derivative. Does that seem right? Oh. There we go. Okay, cool. So the next step though is that, let's see, how does Andrej motivate it? The idea is that okay, so what does he do? The first thing he does, okay, is remind us numerical derivatives. That's fine. More of the same. Okay, before he starts writing value, I want to see exactly what he said. And I'm going to turn on this too. It might make a little echo, but it's worth it.
Of that b by a little bit in a positive direction, we'd get different slopes. So what is the influence of b on the output d? So if we bump b by a tiny amount in a positive direction, then because a, so and now what is the sensitivity? What is the slope of that addition? And it might not surprise you that this should be 2. And why is it 2? Because d of d by db, differentiating with respect to b, would give us a. It gets bounded. And now c simply adding c. That tells you that the slope is 1. That will be the rate at which d will increase as we scale c. Okay, so we now have some intuitive sense of what this derivative is telling you about the function, and we'd like to move to neural networks. Now, as I mentioned, neural networks will be pretty massive expressions, mathematical expressions. So we need some data structures that maintain these expressions, and that's what we're going to start to build out now. So we're going to build out this value object that I showed you in the README page of micrograd. So let me copy paste a skeleton of the first very simple value object. So class value takes a single scalar value that it wraps and keeps track of, and that's it. So we can, for example, do value of 2.0, and then we can look at its content, and Python will internally use the repr function to return this string. Oops, like that. So this is a value object with data equals 2 that we're creating here. Now what we'd like to do is we'd like to be able to have not just like 2 values, but we'd like to do a plus b, right? We'd like to add them.
Okay, all right. So it is pretty transparent. It's basically the point of the value in the first pass is to construct is to have a data structure that stores a DAG. So it wraps a mathematical expression but with provenance. It keeps track of, okay, so that makes sense. So we can delete all this. This is all just, I mean, I remember how to take derivatives, you know. I'm not, you know. Anyway, so let's just delete this and all of this. Delete this. So the first thing I'm going to do is have a struct called val, and it's just going to have data, which is an F64, and that's it. And actually, I mean, we can already kind of go to this. We're going to vec of value, and I think when we start to do prev, we already immediately see how things fail. So yeah, keep it val. Actually, let's just keep it value. And then the other thing that we definitely need to store is an op, which is an op. And I'm going to just, instead of storing a string Rust, we're going to store an enum that we can match on, and that's just like way better. So I'm going to have a leaf node, which is like just a raw number pretty much. Then an add and a mul. And that's all we're going to have for now. We really don't need more than that. Okay, so the point here is that, well, first, maybe I will do this. So this is like to keep your head in the game of the point of value for now is not even about gradients, although it will be, and it'll be a pretty simple extension y. But just to, if I have an expression, and let's say that I have an expression like this. Let a equal 2. Let b equal -3. Let c equal a plus b. Let d equal c plus a. Okay, so we have an expression like this. And what we want to do is basically build a graph. And it just so happens that the directed graph is acyclic, which is called directed acyclic graph, which is a DAG. And we want to build up a data structure that that stores basically this tree, and that's what the previous will be. And I'll just say I'll keep it prev, but it's the children of this DAG. And so we want a way to do this. So the first thing we're going to do is wrap. So so what I'm going to do is wait, can't I? Yeah, there we go. So this is how you implement those infix ops on a data structure like in Rust. So first we have to do this thing, which just parameterizes what the output, because it may not be that the add of a val, and implicitly this does this. But you don't need to do that because it like does it for you. So then we write here, and I think actually I wonder if I do, let's say, some random type. If I write this, and then I write this, see how it wrote I8 here? So the Rust analyzer is helping us understand how things are working. But for right now, we just want to add 2 values. Okay, and all we're gonna do is basically make a new. Oh yeah, and I should probably do an. And we're just going to do value data, and that's it for now. And so here it's just going to be value new, and it's going to be self.data plus right hand side data. Okay, so now the next steps are we're just going to wrap this in value new. Okay, and let's just see if I can print out C. And this errors because we did not implement display. And so I think what we want to do is derive debug. I think I have to do this. Okay, there we go. So what we basically did is we did 2 minus 3, or 2 plus minus 3, which is minus 1. But we did it by wrapping a struct around it. And one thing to be absolutely clear about is when we do A plus B, C is a value, and it's a new value created in the add. So right now I'm not even going to do mul. I'm just going to keep it as add. And one thing that we may want to do is we would now want to store the previous and the op. And so what I want to do is that when I add 2 values, so I guess I can keep leaf new as a leaf. It's just a, but then I can write like with previous. And so here we're going to get a data, which is an F64. And then we're also going to get prev, which is a vec of value. And we're also going to get an op, which is a op. And we're going to return a value. So I can do self. All right. And the point here is that it's just going to be value, data, prev, op. And that's it. And then here I can do this. And this is going to be data, this is going to be an empty vec, and this is going to be a op leaf. So what leaf means is that it's the value has no children. Okay, so that makes sense. So now what we want to do here is with prev, and we want this data, but then we also want a vec of self and right hand side, and then we also want op add. Okay, so now if I run this again, debug is not. Oh, wait, how do I do this again? Hash derive, oh yeah. Okay, here we go. So now we've added it. We've added two numbers, but we've also tracked what the where this node came from, and it came from the result of adding two leaf nodes together. Okay, so now maybe add mul. So let's just try this. Actually, do I want to add mul? So now here's the part where my familiarity and understanding of Rust kind of crashes and burns. So one thing that I want to try is instead of doing this, expected a value. Okay, wait, but if we just said instead of that, this is a vec of a reference to value. So the point that I'm trying to make here is that if we make them all references, then this still does not work because of lifetimes. And so the way to make this memory live longer, and let me just confirm this. Okay, so in micrograd 2, the folder, I have the skeleton of basically a struct that starts to have basically store within it a DAG in the sense that it remembers where it came from, i.e. if a node or if a value is the result of an addition operation, we store what the children were and what the operation that produced this note is. Now, I'm trying to remember the motivation of what of the lifetime, because the current error is about. So first, I just naively said value is stores, a piece of data, which is just a float, 64. Prev, which is a vector of values, owned values, not reference, even though the current implementation has reference. And an op, which is just an enum that has either it's a leaf node or it's an addition. That's pretty simple. Then I implement the add trait on value, not ref value, not reference value, but just value. And I do the obvious thing where I basically construct a new node whose data is the result of the addition, and the previous, which is the two components of the addition. And then when I started to construct my DAG in the main function, I get data moved error because I passed in A, I guess, into C when I did A plus B. And so then when I tried to use A again in the construction of D, it says this memory moved, and so you no longer have access to it. And so the next logical step was, okay, I'm just going to make everything references. So prev is now going to store a vector of references to value, and add is going to be implemented on references to values. But now I get lifetime errors, and I'm again trying to remember the logic of I should be thinking, okay, I need to use reference counting, and that's the part where I'm not strong on. Right, because now we're seeing cannot add value to value, but let's try this. This works, but now we say, okay, we need to know how long this, but can I just do this? If I just make everything static, right? But if I did this, right, it only works on a static. Right, so I could okay, owned predecessors, vec of val. The output node exclusively owns its input nodes. Right. Yeah. Which you clearly don't want. So when you perform A plus B, Rust moves A and B into the resulting node. So after C owns C, this representation works for an expression tree where every node is consumed exactly once. It cannot. So if you had a true tree, actually that'd be totally fine. But because we have a DAG where data can be used potentially more than once, you can't do this. All right, so then you get to borrowed predecessors. The output doesn't own its input. It temporarily refers to nodes owned elsewhere. Now, C depends on A and B remaining alive. That dependency must appear in the type. The compiler's current error is asking you to express I gotta shift. All right. Okay. The lifetime does not keep A or B alive. It records the restriction that C cannot outlive A or B. This can be made to work for carefully scoped stack graphs, but it becomes awkward. Every value gains a lifetime parameter. Every operation must relate the input lifetimes. This is why RC removes the lifetime problem. The edges own handles rather than borrow someone else's storage. Okay, so I think probably the thing that I skipped over yesterday was, so the conceptual structure. Separate the node from a handle to the node. Right, so now, so we're getting into, you have a value which is the reference counted thing that passes out shared references to nodes, but nodes are the actual data. Later, gradient mutation adds another requirement. RC permits shared ownership, but normally only shared immutable access. That's where ref cell enters. So we're not even going to do ref cell. So yesterday I actually skipped over this important part. Wait, but if I did this, my local A cannot. Oh, so static? Yeah, okay. Program start main begins when instruction on A is created. A real static item exists independently of any stack frame. I see. A is still stack owned. Okay, alright, I get it. Alright, so let's undo all the static stuff. I feel like that was a thorough explanation of why staticking everything is not the appropriate thing. So the next step is going to be doing this. It's going to store one piece of data, which is a node, which is an RC reference code. And then do I still need a... Oh, yeah. I always do this. This syntax is so fucking annoying. Okay, so here's the deal. We want the previous to not be nodes. That would defeat the whole purpose. We want it specifically to be value. Okay, now all we have to do is value node like that. Oh yeah, and we just have to do RC new like that. I think that's it. And then prev, I think we just do this, right? Oh, what's up, Mohammed? How do you learn all by yourself? Isn't learning by yourself is not so efficient? That's a complicated question. I think modern AIs definitely changed the picture. I think you probably can learn extremely efficiently on your own. At least I find that to be the case. Now, one factor that's not really included in the calculation, or at least something that I didn't fully appreciate for a long time, is if you can convince yourself that getting a good grade... Well, okay, wait. I will say, rather, the factor is, can your teacher inspire you and convince you that the material is important enough that you really have to do well? And so your motivation isn't getting a good grade. It's inspiration. It's that your teacher has inspired you to see why understanding this thing at a deep level is important. And as a result, and so I think that that is an important factor, is that other people can help show you the context of the material in a way that I think is maybe a little bit obfuscated, or at least deprioritized when learning by oneself, is a lot of times you're thinking you're gonna learn something and you already understand its importance or something. So, anyways, I don't know. Okay, let's do this. Node.prev should store a vec of value because value is now your cheap clonable handle. So hold on. Oh, that would make the graph bar local value handles. Okay, that is the that's the truth right there. Oh, but you know what's interesting is expected a value but found a value does not implement clone, but isn't it? Then I probably need to put clone on this, right? No. Expected a raw value. Wait, what? I did clone. Something is weird. Hold on, I'm gonna go to the bathroom. Okay, so let me just try to vocalize what it is that I'm trying to do. I'm trying to update the code that adds two values. And I think don't I want to get rid of this? I think I want to get rid of this. Takes ownership of self, which moves self. So should I just do this? I think that works, right? So we just clone both times. So wait, let me think about this. But can't I just do this? Because the output must retain its present switch after add return. Add clones the value handles. Okay. Okay, so what we're going to do is do this. Wait, actually, I'm just going to undo all of that. So we're going to implement this for value, implement this for value. Then this is going to take just a reference. And that's it. And we can actually, I think I can just do this. So that doesn't clone its children's. Okay. Alright, cool. Good stuff. So, where are we at? It's always good to contextualize. So now we have the ability to add and store the DAG, which is good. Now I want to add grad, I think. Oh, wait. Okay, so wait. My feeling is the next step is grad. Alright, let's do mul. I'm down to do mul. Okay, so we're going to add another op. Then we're going to do this. So let d equals c times a. Now we say cannot multiply value by value. So we're going to do then impl mul for value. Self. Can I do that? So self is this. Okay. Alright, so here's what we're going to do. It's basically this exact same thing, except this is going to be a times, and this is going to be a mul. And so now we have added the ability to track mul. And I think now oh yeah. Okay, so it's time to add grad. So grad is the gradient. And so wait, so this expression is, you know, a plus b times a. So this should be equal to 4 minus 3 equal to 1. And this should be equal to 2. Okay. So now we've manually gone through, and for this DAG, But what we want to do is we want to go intermediate too. So dd dc is equal to a, which is equal to 2. And then dc dA is equal to 1. dC dB is equal to 1. So D is equal to minus 2, right? Let me just do this really quick. Yeah. Okay. Oh wait. No, minus 1. Okay, so we've now added empty grad field. So grad is 0 all the time. And now I can do something cool, which I'm just going to... then I think I just do mod dot, right? I don't actually know how any of this works. Yeah, mod dot. Okay, so what this code is first we have a way to render an op into a piece of text. And then here this just builds a graph. But we want to see if I can just do this for now. Instead of a bar, let's just clone it. Okay, then I should be able to do... let me just copy the code, because it's not like... I mean, it's definitely interesting, but it's not the purpose of this. And all I want to do is render graph and then print the... Okay, that's all. I'm not touching that code again. Okay, cool. So now I should be able to, in target graphs. Alright, cool. So now we have a way to look at DAGs, which is going to be very useful. Okay, so those are just a couple of helpers to get the ops and get the whatever. The important point now is I'm going to try to implement a function called local backwards. So the okay, and I'm going to think about what that exactly means. The first step that I want to do, though, is before I do any of this, I want to say d.node.grad is equal to 1. And then this should error because it says Cannot assign data to an RC. Trait deref mute is required to modify through a dereference. Okay, so either I can implement this trait deref mute. Okay. So this is the part where I'm like, okay, cool. So now we've added this ref cell thing, and the cool thing about the ref cell is that it lets us mutate nodes, basically. Okay, so now I'm going to write this, and this is going to take a self. It's going to take a self. Let me think about that. So what is this function going to do? This function is going to assume that, so it's going to have, let's just say it's a self. I don't know if it's a self or a reference to self. And it's going to return nothing. And what it's going to do is going to look at its children, and it's going to update the gradients of its children by applying the chain rule locally. So what we do is we assume okay, now here is the real crux of this thing. if it's an addition, so if we reach this plus node and we have this gradient set, what we want to do is we now want to look at our the children, and we want to set them equal to self.grad times 1. So for child, or actually I think I should be able to do this. I think I just borrow the node, but then I iterate and I borrow mute. That's what I'm trying to do this. Okay, so we take its node, the node, we borrow it, we look at its predecessors, we iterate over them, and for each of them, we borrow it as mutable and set its gradient to 1 times g. All right, now let's do mul. So first we're going to say, so we have g, so now we're going to let, all right, so what do we have? We have we want to get the children, right? So we want to get this. So and I'm going to do this. Left hand side, right hand side equal to of type slice of value 2 or 2 is equal to self.node.borrow.prev.try into .unwrap. Cannot move at a dereference. Consider cloning the value. So I think I can just do this. .clone. Alright, so now we have the left hand side and the right hand side. And what we want is we want the data. And what we're going to do is we are going to set the gradient of the left hand side. So left hand side dot node dot borrow mute dot grad is equal to, and it's going to be g times rx, which is the right hand side data. And the one thing, though, that we have to do here that's important is we actually need to make this a plus equals. We need to make this a plus equals and this a plus equals. Because when we have multiple paths here, it's an issue. So what I want to do here is I actually want to call d dot local backwards. And I think we just want to give it a reference. I think we just want to make this reference. Okay, and we can see here that this gradient is now -1, and this gradient is 2. And now what I want to call is c dot local backwards. And we now have the gradients, I think, are all correct. I'll do it manually in a second. Okay, cool. So let me just check. 1 and 2. DC is 2. So we're good. So this is correct. All right, nice. The next step is to implement the full backwards. And the way to do this is gonna take some more thought. You're arranging nodes so dependencies occur before the nodes that use them. Consider a more revealing graph. So we have u is equal to 2x, v is equal to 3u, w is equal to 4u, and L is equal to v plus w. So if we accumulate here, v is equal to 6x, w is equal to 8x, L is equal to 6 plus 8x equal to 14x. So dl dx is equal to 14. dl dw is equal to 1. dl dv is equal to 1. dl dl is equal to 1. Then we do dw du. Oh, okay, yeah. So say we visit V. So V is now going to set So I don't think we need an example quite that complicated. I think a Okay, so let's go through this slowly and step by step. The first step is that W, and can I do this? I think I can do this. Okay, so we set this gradient to 1, and then we're going to local backwards on both of these. Okay, so I can just do that. So, okay, and these get 1. Now the point is, oh yeah, we actually need the main thing is we cannot visit a node. This is the main constraint. We cannot visit a node if we haven't visited all parents. Yeah. Because we will update X's children on incomplete faulty info. Okay, so the way to do this Okay, let me see if I remember how to do this. So in here, I have to actually do two functions. So function, this is going to take a v of type value, and it's going to return a vec of value in sorted order. Now what we're going to do is we're going to construct a let topo equal vec, or vec. Let visited equal a hash set new, and it has to be mute. Let mute. Then we're going to write a function called visit, and we're going to visit, and it's going to take a value. It's going to take a reference to a mutable. It's going to take a visited of type mutable hash set value. And then finally topo, which is a reference to a mutable vec of value. And it doesn't return anything, it just does it. Okay, and what we are going to do is we are going to call visit on v with visited topo. And then we're going to return topo. Okay, so the first thing we're going to do is we're going to check if visited contains. Why doesn't that work? Hold on, I'm just going to check really quickly. Oh. Oh, because we don't have eq. We don't have eq, then. But okay, wait. But if I just derived. Can I just derive eq? So I don't think we want to do that. But yeah, so it needs to be a U size. I forgot about that. And it's going to be. The way that we do the identity of a node is we actually look at its pointer. So we take the RC and we do as pointer. And it's just going to be v.as pointer. Right? Oh, I have to cast it? Oh, and oh, wait, hold on. V itself is not, okay, first off, V itself is not an RC. So what we have to do is v.node, now that's an RC. We can now do that as pointer. But the thing is, as pointer returns a raw pointer. So we need to cast it. And then we need to dereference it. Okay, that's enough of this. No more cheating. But this is all like really janky, and it's like so if we haven't visited this node before, then we are going to first say that we visited it. So visited the insert. Oh wait. Visited dot append. Dot push. Okay, that push v or v pointer. And then for child in we are going to call visit on child with visited and topo. So okay, so think about what's happening here. So we say we visited it, but we haven't actually done anything to the list. And then we're going to the children, and we're going to visit those children. I think I just can clone it, right? I don't know. I'll check the answer later, but I always forget this stuff. This stuff always bothers me. Let me read this error again. Cannot remove dereference. Can I try to write it more functionally? Like v.node.borrow.prev.forEach. Then only after we visit each of its children can we add. All right, so we go here. We say it's visited. And we add it to the visited list. Then for each of its direct children here, so we start here. Then we say that's visited. Then we go here. So this is visited. Then we go to both of these. Okay, then we say this is visited, and then we push it. So topo.push v. And it's probably have to clone it. I don't know. And I think that might be it. So then this gets on the topo first. Then we go here, and we go to these. Then we visit. So we visit this. Then we go here, visit this, append this, visit this, append this. Then we append this. Then we append this. Then we go here, visit this, visit this. Oh no, check if this has already been visited. So no, we skip that. Then we visit this and append this. Then we append this. and then we append that. So I think that's right. And then all we have to do is say topo.reverse topo. So then we can finally implement the function backward. The function backward. Is it backward or backwards? Backward. Wait, backward or backwards? It's backward. Backward. And so first, what backward is going to do is it's going to first do, it's going to take a self, presumably a reference to self, and then it's going to do self.setGrad to 1. Then it's going to say let topo equal build topo of self. Do I need a dereference? Or, okay, let's clone it. I honestly, it gives you so much help that you don't even need to concern yourself. Okay, then for, then okay, now I want to try this. So now, let's go back to this, make this D, get rid of this. And instead of doing all of that, we're just going to call D.backward. Okay, so now it's time to eat some breakfast and then finish up the neural network library part of this stuff. But that was fun. That was really, really fun. Oh, wait. Dude, I am convinced that I'm never getting this Buchner funnel. Should I just do this right now? Should I just filter it off? No, I'm not going to do that. I don't want to do... Oh, it's out for delivery. No way. I just got this notification. I was literally... Oh, it put me so far behind. Okay. All right, so now I have a working backprop algorithm, and now it's basically time to add more things. And all I have to do is do I really have to do this? That's hilarious. Ooh, look at that. Wait, but... Let me think about this. How can I make neg? Oh, we don't even want neg. Right. We don't even want this. So what's next? Let me actually...
We're going to store how we are going to chain the outputs gradient into the inputs.
It's getting chilly. Yeah, okay, so instead of having a sub operation, we are going to implement... Yeah, so you can't even put this as a gate, but I can put this later. Probably have to clone this, right? Oh. Probably still need to clone this, right? Do I really want this? I don't know. Ugh, why do I keep doing that? This is pissing me off. Self.node.borrow .prev .clone I guess first does some weird shit. Chuds. Oh. Oh. Why is the gradient 0? Oh, because it's at 1. It's saturated. I see. Actually, shouldn't I just do this? And then here, I should be able to do just chuds.iter for each. And then here, it's just going to be whoa, what? This I might put here so I don't keep forgetting. I need POW. POW is kind of the last one I need, right? Is there impl POW? I don't think there is. Okay, let me just try. So this, I'm going to implement as a POW, and this is going to be I mean, I probably do, right? I probably need this to be a value. There is no integers, but the problem is I need to have an integer. But presumably it would be with prev self.data dot pow f exp.data, and then pre-vec of self.clone exp.clone, and that's it. And then op is op pow. One problem with this is you don't know which. In this graph, it doesn't tell you exactly the order, which is a little bit stupid, but I mean, it's whatever. So it's saying to do like that. That's interesting. We store it in the op. That's kind of weird, but that's cool. So instead of doing all that, it's just going to be just this. Oh, it needs to be I-32. So that wasn't the problem. So I think I have everything that I need. Oh wait, POW doesn't have its so it's going to be it's going to be x times self.data.pow I x minus 1. That is it. So it's going to be wait, G is an F64. That's it? Okay. Okay, so now it's time to do some neural network stuff, right? So
Ingredients. So by default, so we have one last piece to get rid of, which is us calling reversed. The gradient here is not actually correct, that we calculated automatically. And that's because Of course, prove to you that you get all the same results and all the same gradients, but also because it forces us to implement a few more expressions. It forces us to do exponentiation, addition, subtraction, division, and things like that. And I think it's a good exercise to go through a few more of these. Okay, so let's scroll up, things like that.
So if I wanted to redo this, I could do Oh, actually, wait, why don't I just do this? And then if I wanted to do I would just so now I don't even need to, oh, but I want to do this. I probably want to template this out for all of this, right? And that's pretty interesting. Okay, good. So now I have that. So now I should be able to just do... Why is that wrong? Oh, because it's an integer. Okay, that's okay. Wait, what? I thought I did it. So I need to do this. Ugh. That's insane. Oh, but I don't even need to do this anymore. Oh. Oh, look. See, okay, wait, hold on. In the local backwards function, we say self.data, but self.data is x to the y, not x. So we actually need... Now we're getting big graphs. Big graphs. But this branch should never get hit now. Because when we call tan H, now we add a bunch of stuff. All of this. Can we go on a short walk? Let me get a shirt. All right. So the next step is definitely to get
I think it's a good
into.
exercise to go through a few more of these. So redefining, we should now be able. So this function will be called when we try to. So now I would like to show you how you can do the exact same thing but using a modern deep neural network library, like for example PyTorch, which I've roughly modeled micrograd by. And so PyTorch is something you would use in production, and I'll show you how you can do the exact same thing, but in PyTorch API. So I'm just going to copy paste it in and walk you through it a little bit. This is what it looks like. So we're going to import PyTorch. torch. And then we need to define these value objects like we have here. Now, micrograd is a scalar valued engine, so we only have scalar values like 2.0. But in PyTorch, everything is based around tensors. And like I mentioned, tensors are just n-dimensional arrays of scalars. So that's why things get a little bit more complicated here. I just need a scalar valued tensor. Torch, for example, is a single, and so Python. So it's, we have by default now by gradients for leaf tensors. Make sure that PyTorch knows that they require gradients. Now by default these are set to false, by the way, because of efficiency reasons. Because usually you would not want gradients for leaf nodes, like the inputs to the network. And this is just trying to be efficient in the most common cases. So once we've defined all of our values in PyTorch land, we can perform arithmetic just like we can here in micrograd land. So this will just work. And then there's a torch.tanh also. And what we get back is a tensor again, and we can, just like in micrograd, it's got a data attribute and it's got grad attributes. So these tensor objects, just like in micrograd, have a .data and a .grad. And the only difference here is that we need to call a .item because otherwise PyTorch .item basically takes a single tensor of one element and it just returns that element, stripping out the tensor. So let me just run this, and hopefully we are going to get, this is going to print the forward pass, which is 0.707, and this will be the gradients, which hopefully are 0.5, 0, negative 1.5, and 1. So if we just run this, there we go, 0.7, so the forward pass agrees, and then 0.5, 0, negative 1.5, and 1. So PyTorch agrees with us. And just to show you here, basically, here's a tensor, I'm on it to just get the single number out. And it's got, so like x2. So basically, tensors are significant in parallel on all of these tensors. But otherwise, what we built very much agrees with the API of PyTorch. Okay, so now that we have some machinery to build out pretty complicated mathematical expressions, we can also start building out neural nets. And as I mentioned, neural nets are just a specific class of mathematical expressions. So we're going to start building out a neural net piece by piece, and eventually we'll build out a two-layer, multi-layer perceptron, as it's called, and I'll show you exactly what that means. Let's start with a single individual neuron. We've implemented one here, but here I'm going to implement one that also subscribes to the PyTorch API in how it designs its neural network modules. So just like we saw that we can match the API of PyTorch on the autograd side, we're going to try to do that on the neural network modules. So here's class neuron. And just for the sake of efficiency, I'm going to copy-paste some sections that are relatively straightforward. So the constructor will take number of inputs to this neuron, which is how many inputs come to a neuron. So this one, for example, has 3 inputs. And then it's going to create a weight that is some random number between -1 and 1 for every one of those inputs, and a bias that controls the overall trigger happiness of this neuron. And then we're going to implement a def __ call of self and x, some input x. And really what we want to do here is w times x plus b, where w times x here is a dot product specifically. Now, if you haven't seen call, let me just return 0.0 here from now. The way this works now is we can have an x, which is say like 2.0, 3.0, then we can initialize a neuron that is 2-dimensional, because these are 2 numbers. And then we can feed those 2 numbers into that neuron to get an output. And so when you use this notation, n of x, Python will use
Oh, you do. I do. 0 0 dot dot n in dot map. Oh, but this is not. Very interesting. Okay, so now we have a neuron. But I want to see how he does the rest of it. So the first thing is
call. So currently call just returns 0.0. Now we'd like to actually do the forward pass of this.
to make a struct callable. Oh, impl. You impl.
Neuron instead. So what we're going to do here first is we need to basically multiply all of the elements of W.
Oh, and then he just manually he doesn't make it generic over the yeah, that's fine. Okay, so so wait, I want to learn how to do the trait thing. That's pretty cool though. So it's gonna be dot. Do we have a dot product? What is this? This is something else. Well, but these are values, right? But it's still a dot product. I call. Iter zip map fold. Dude, that is insane. Is that really? Bro, that's insanity. Okay, so I was right. iter.zip.map AB or WIXI, and it's just going to be WI times XI. But the thing is, the inputs aren't necessarily values, right? The inputs aren't values. The inputs are well, okay, so I guess before I call it, I have to do it manually. But that's fine. I don't really mind that. Okay, then dot fold. And then some product. Do I have to wrap that? No. And it's so it's going to start at the bias, and then it's going to go to the first one, and which is going to be this. It's going to add that. Then it's going to keep. Then it's going to go to the next one with that stored, that accumulator stored. Okay. So it was a fold. I knew it was going to be a fold somewhere. All right, so there's that. And then can't I just do... So that's a VECA value. Wait, no. This whole thing, we want to just do .tanh. Okay, so that's the forward pass for a neuron. Okay, I gotta get going. Okay, so that's the forward pass of a neuron. I feel like that's a good place to end. I mean, ideally I implemented a little bit more of the neural network, with layers and all that stuff, but an MLP. But that's pretty good. Dude, I love programming Rust. So fun.